All right, we're in the final chapter for this course, chapter 9, and this is a relatively short chapter for us. We're only going to cover the first two sections, 9.1 and 9.2. The focus in this section is on numerical methods, and we've talked about one numerical method for finding approximations for for initial value problems. Way back towards the beginning of the course when we introduced Euler's method. And back then we saw that Euler's method is a technique for approximating a specific point on the solution curve for an IVP given a first order differential equation and an initial condition. And we saw that it uses the idea of like computing a sequence of tangent lines. We even provided, I think, an image of a graph that kind of showed, graphically what's going on in Euler's method. And I think I mentioned back then, but Euler's method, even though it's the first numerical method that everybody learns in a differential equations class, it's also one of the worst as far as accuracy goes. The benefit of Euler's method is that it's straightforward to learn. So it's straightforward to see why it is an approximation tool, and it's computationally relatively simple. In numerical analysis, we would say that it's an algorithm with a low cost, meaning it doesn't have to perform several complicated computations every step or every iteration. So for that reason, it's a fast-running algorithm, but it's not. The trade-off is that it's not very accurate. So what we're looking at here, 9.1, is an improvement on Euler's method. And before we get into that, we're going to talk about something that we always need to take into consideration when we're looking at numerical methods, which is error analysis. So we're going to start there. Now, this is just a reminder of what Euler's method's formula looked like. Remember, you have to have a first-order equation, and we're only going to be dealing with first-order equations in these first two sections of Chapter 9. But you have a first-order equation, and it has to be put into this form. Y prime equals some function of x and y. You have an initial condition, so that you're looking at an IVP. And Euler's formula is given by this recursive formula. And remember, this is graphically, this is just like computing a sequence of tangent lines that are being used for approximation. Okay? So in numerical analysis, which is the area within math that studies these numerical methods, there is a very important thing that we have to look at called error analysis. And all that is it's a way of looking at what kind of error can creep into a numerical method, and then that opens the door for trying to mitigate that error and trying to make our algorithms more accurate. So error comes from a number of sources, and one particular source that error comes from in these algorithms is what we call round-off error. And round-off error is something that is directly the consequence of technological limitations in calculators and computers. So in computer science, a computer or a calculator is modeled by something that we call an FSM, which stands for finite state machine. And what that means is that, at least in the context of these numerical algorithms, when a computer or a calculator is working with a numerical value and is trying to store some kind of decimal representation for that, it's incapable of storing an infinite string of digits because it's limited by its memory. So for the purpose of computations, computers will take decimal numbers that are normally represented by an infinite string of digits. For example, the number 1/3 as a decimal looks like 0.33333 repeating infinitely. We say that it's a non-terminating decimal. A computer will have to cut that string of threes off at some point. And in effect, what it's doing is it's rounding that number. Then when that number gets used in a sequence of computational steps, it's introducing error into the results of those computational steps simply because it's working with a rounded value. And the more steps that algorithm takes, in general, the error compounds every step of the way, making the error bigger and bigger and worse. So that's, like I said, that's what we call round-off error. And because that's due to technological limitations, and there's usually not a whole lot we can do as far as changing an algorithm to mitigate that kind of error, we're not going to be focusing on round-off error here. We just wanted to define it so you know one source of error in these numerical methods. Okay, the kind of error we're going to focus on is something called local truncation error. And to understand where that comes from, Euler's method is like most numerical methods in differential equations. Most of these approximations are done using an iterative formula, so a recursive formula where we feed it some initial value that provides an output, and that output is fed back into that recursive formula, providing a new output, and it's kind of this loop of feeding outputs back into the formula until we get to the approximation that we're looking for. If we focus on just a single iteration of that process, let's suppose that we have some value that's being used as an input into that recursive formula. Let's call it yn. And for the purpose of this type of error, let's assume that we're starting with an exactly accurate value, which an initial value would be. So if we're talking about y0, that would be initially exact. Once we feed that into our recursive formula, we get an approximation for the next number in that sequence, y of n plus 1, or yn plus 1. And usually in that first step, this approximation is not going to be exact. Usually it's going to be off, even if just by a little tiny bit. The amount by which this first approximation is off is what we call local truncation error. This local truncation can be positive or negative, but in our error analysis, we're going to end up taking an absolute value so that we think of it in positive terms. Now let's look at how we can evaluate or try and understand the local truncation error of Euler's method specifically. So what we do is we assume that we're working with a function y of x. This is the solution to our dE that we're trying to approximate. And let's suppose that it has k plus 1 derivatives, all of which are continuous on some interval containing these two numbers, a and x. Okay, toward the end of Calculus 2, like at the very end of Calculus 2, you introduce something called Taylor's theorem. Taylor's theorem is a representation of a function y of x in terms of a Taylor polynomial for that function, plus what we would call a remainder term. And Taylor's theorem is actually mostly concerned with this remainder term. So Calc 2 is a prereq for this course. I'm not going to go through a big review of Taylor polynomials, especially since we're not really going to be doing much with them directly in this. But the function y of x, if it has k plus 1 derivatives continuous on that interval, then Taylor's theorem applies as far out as the kth derivative here. This is what the kth Taylor polynomial of that function y of x about the number a would look like. Okay, so that's the Taylor polynomial. Now the function itself, if it's infinitely differentiable, can be represented by a Taylor series. But because we're cutting that Taylor series off right here, the remainder of that series is going to account for that error. Taylor's theorem takes all of that and summarizes it with a single term. So this term right here, this remainder term, is where we get the error in these numerical methods. And we'll look at the specific case of Euler's formula in a second. But just to revisit, from Calculus 2 what this remainder term looks like, notice that it's the k plus 1th derivative of y evaluated at some number c times x minus a to the k plus 1 over k plus 1 factorial. Now this c here, it's important to know what this c or what it is, where it's coming from. C is generally going to be some unknown number, but it's according to the theorem, will always lie between a and x. Okay. Now, the reason it's important to know that it's an unknown number, it's simply something that we know exists, but there's not really a reliable way to find it, is that if we could find C directly, then we could plug it in here, subtract away this remainder term, and get an exact value for y of x, which kind of defeats the purpose of approximating. So in general, we don't know how to find this C, but we just know that it exists. Now, let's plug in some specific values for k, a, and x in this this equation here. So if we set k equal to 1, remember k is the number of derivatives I take before I get to my remainder term. If I set that equal to xn, which remember that would be the nth, or that's one of the inputs that we would be using in our recursive formula. And if I set x equal to the next number in that sequence of x values, xn plus 1, think of what this would look like if we plugged that in. So x is equal to xn plus 1. I'm plugging that in here. That's the only place that x appears. Well, actually, so it also appears in these values up here. But that's y of xn plus 1 would appear there. Y of a, we're setting a equal to xn. So this would be y of xn, which using the notation that we talked about back in Euler's formula, we call that yn. Remember, yn is the output that we get from plugging xn into our recursive formula. Then, up here, what is x minus a? Well, x minus a is xn plus 1 minus xn. But the distance between these two numbers is what we define to be our step size in Euler's method. So the difference is that number that we were calling h before. 1 factorial is 1, so we can kind of just get rid of that. And then y prime of a, well, remember, y prime is related to x and y by the differential equation that we start with. Y prime is equal to this function of x and y, so we can call that f of xy. And in this case, we would be looking at f of xn, because xn is what a is equal to, and the corresponding y value that goes with that is yn. Okay? Now look at this, yn plus hf of xn yn. This is exactly Euler's formula. So Euler's formula arises from the first two terms of that Taylor polynomial. And together, in our recursive formula, this would be what we call y of n plus 1. Okay, remember, y of n plus 1 is what we'll be getting from substituting xn into this recursive formula. And then if this is the true value, y of xn plus 1, and this is the approximated value, yn plus 1, then this thing right here would represent the error. It's how far off our approximation is from the exact value. The trouble is that, again, like I said before, we don't know exactly what c is equal to. All we know is that it lies between, in this case, xn and xn plus 1. And then we have this h squared over 2 factorial. Again, the h squared, in this case, if we set k equal to 2, or sorry, k equal to 1 right here, so that this is y double prime, this would be equal to x minus a squared. Remember we said x minus a is the same thing as h. 1 plus 1 factorial is 2 factorial, so that's where that error term is coming from. Even though I don't know what c is, I can find an upper bound for it at the very least. So what that does is if I can find the absolute largest value that y double prime of c can be equal to, then I can put an upper bound on that error term. I can find the maximum possible value of that error, and that is useful to know. So again, remember c lies between xn and xn plus 1, and if we can find the absolute value of an f double prime of x and find the maximum value of that using all of the numbers in the interval of real numbers between xn and xn plus 1, that would represent the absolute largest in absolute value that this number can be, right? So if we call that maximum number, whatever it is, capital M, then I can substitute an M in here to get the maximum error, so that the maximum possible local truncation error for Euler's method is M times h squared over 2 factorial. Okay? Now, this is where we kind of start to see that using a smaller step size gives us more accurate results, which we talked about back in Euler's method. Because if h is smaller, that's going to shrink the size of this maximum truncation error down, giving us a better result. Okay? But that's not the only thing that would really reduce that error. See, we're squaring h, and if you imagine h to be a small number, less than 1, then raising that number to a large exponent produces an even smaller error here. So if the exponent on h can be made bigger than 2, then the error will be made smaller, because we're assuming h is a small number. Generally, our step sizes are smaller than 1. Okay, so we now want to look into a way of increasing the size of that exponent on that h there. And to do that, we're going to introduce some notation. So when we do error analysis for any kind of numerical computation, we're going to use this notation E of h to represent the error term, or the numerical error that's produced by that algorithm. And notice it's a function of h. It changes depending on our step size. So for Euler's formula, for a given function where we could determine this capital M, h is the unknown here. We could change our step size and then change this error term accordingly. Now, if there exists any constant capital C such that that error term in absolute value is bounded above by c h to the power of n for a sufficiently small value of h, then we say that the error term has an order of h to the n. And we denote that by something that we call big O notation. So numerical analysis, again, that's a course that you could take. It's upper division math and graduate level math if you ever wanted to major in that. You would learn much more about this big O notation here. But this is something we talk about anytime we're looking at numerical algorithms. And the goal is to get that n to become large so that the overall error becomes small. Okay, so in our case, let's look at what exact effect changing the size of h has on an algorithm that has an order of h to the n. So let's suppose that we've evaluated our algorithm using a step size of h. And then let's say we rerun that algorithm, but we take half of that step size, h. What will that affect as far as the error term is concerned? Well, the maximum local truncation error is bounded above by this, c h over 2 to the n. Remember, that's how we defined that big O notation. Distributing that n in, I get ch to the n over 2 to the n. Ch to the n is the upper bound for my error when I use h as my step size. When I shrink the size of h down by a factor of 1/2, then that takes the error, the maximum possible error, and divides it by 2 to the n. And if n is large, that's a significant improvement in our error. Okay, so that's more reasoning for why we want n to be large if possible. So again, local truncation error, that's what we're talking about here. Now there's another term called global truncation error, and the idea behind global truncation error is that we're looking at the overall accumulated error over several steps of our algorithm. So for example, if we are working with an IVP that has an initial condition, let's just say y of 0 equals 0. And we're trying to approximate y of 0.5, which is actually the example that we're going to do in the next video. And let's suppose also that we wanted to use a step size of 0.1. Well, to get from 0 to 0.5 with a step size of 0.1, you have to go through 5 iterations of your algorithm. And our local truncation error only looks at one iteration of that algorithm, and it also assumes that the first the initial value that you're starting with is exact. So it doesn't really answer the question of what the total error will be over the entire run of that algorithm if it takes multiple steps. Global truncation error does describe that, but in analyzing that requires things that are beyond the scope of this course. So we're not going to talk about that here. I just wanted to give the definition. Okay. Now that's our discussion on error. We're going to get into the improved Euler's method in the next video, because I think we have gone long enough for this first video, so let's go ahead and stop this one here.